cubic, these types of variability. And we repeat this process, let's say 1,000 times, or infinite number of times in principle. You get the black line as the average prediction of this model class trained on 7 examples, and the green lines indicate the variance of the predictions, and you can decompose the test error of every test example into bias and variance. Right? And the goal is to choose the model class with the map that optimizes the bias variance trade-off. High variance implies overfitting. The model class is unstable. Variance increases with model complexity, and variance reduces with more training data. High bias implies underfitting, right? For a constant model class, even with no variance, a constant model class this model class can have high error. The bias of this model class, the bias decreases as you decrease the complexity of the model class, and this is independent of the training set size. This concept. Right. So if this is our decision tree, this is our test distribution. The small data points are our test distribution. What we actually want to measure is the error on this test distribution, but we don't observe all of it. Right. Decision trees are low bias, high variance models, unless you regularize a lot, right? But even then, the variance is often much worse than linear models. Highly nonlinear can easily overfit. Very different training. So if we recollect our training set from the same distribution, and they're different, they can lead to very different decision trees. Right? The variance of the model class is very large. Right? So bagging is a method to reduce the variance of a model class, and was popularized initially for decision trees. Right? So what I've written here is simply just the rewriting of the bias variance trade-off. Right? In the ideal setting, right, we have many such training sets, right? We have many such training sets, and then let's say infinitely many. We train a predictor on each training set, and then we average their predictions, right? And if these training sets are sampled independently from the test distribution, then the variance term actually, if our model class is the average of these model classes, if our model that we train is the average of all these models, then we actually reduce the variance while leaving the bias unchanged. If we're able to somehow redraw training examples from the test distribution over and over again, right? So this is obviously not possible, but suppose we were able to do that, and we train a model using each of these new training sets and average all their predictions, this variance term will go to 0 and the bias term will not change. Right. In practice, what bagging does, based on this insight, what bagging does is you have a single training set, right? And we simply resample it. We have a single training set S. We create a sample. We create a bootstrap. That's what bagging stands for. A bootstrap of S called S prime by sampling from S with replacement, right? And then we train a model in this bootstrap S prime, and then we average their predictions, right? So here's what we're actually doing in bagging. We have their test distribution. We have a single training set from the test distribution. We use this training set to create new training sets S prime called bootstrapping, which is essentially just resampling from S with replacement. And then we train a model using each of these S primes, and then we average their predictions. So bagging stands for bootstrap aggregation. Now, because we're not actually sampling from the test distribution, the variance does not decrease sublinearly as we draw more samples, because the S primes are correlated. At some point, the variance won't go down any further. So this is how it works with decision trees. We have our training set S. We generate many bootstrap training set samples S prime by sampling with replacement from S. The cardinalities are the same. They could vary, but typically they're set to be the same. And then we train a minimally regularized decision tree on S prime. So don't regularize this decision tree too much. So these decision trees have high variance, low bias, but that's okay because we're going to average them to reduce the variance, right?
So how do we average decision trees?
I'm sorry?
How do we actually average decision trees?
So for classification, it's simply majority voting, right? For any input example, you run the prediction from all your decision trees, and then you vote. And if more people vote for positive, you vote positive. More people vote for negative, you vote negative. For regression, it's simply mean. Yeah.
For each bootstrap sample, do we usually have some criterion that enforces some fraction of the of S prime to be distinct points?
Nope. It's a sample with replacement. Yes.
Is bagging conceptually same as k-folds cross-validation?
No. There's no validation here. We're keeping all these trees and just predicting their average.
So how about k-fold cross-validation without validation? I mean, just divide.
So k-fold cross-validation is a way of using your data set in a way that you can use all of it to measure your test error, right? I think they look similar because they're all trying to accomplish some notion of statistical reliability, and that's why they look similar. And indeed, all methods that tries to do some sort of resample to accomplish some notion of statistical reliability will look kind of similar. But they have very, very different goals. Yes?
So you have to lower variance somewhat if you take a sample that's smaller than S, right?
Variance increases as the training set size decreases.
But so, if you expect this to generally introduce variance over the average, can you just do this for like every learning model?
You can, but it really only works well for model classes that have high variance and low bias, right? Because it's trying to find this black line, right? And so the black line does best on model classes that have low bias and high variance.
Is there an optimal number of bootstrap samples?
Obviously, because these samples are correlated, if you do infinite, it doesn't actually help you, right? People may have written papers on the optimal number of bootstrap samples under some assumptions. I haven't read those papers, so I can't give you much advice. I can tell you what number I used. I used 500.
Does it depend on the number of points?
I find that beyond 500 it doesn't help that much in most applications. And so here's just an example from this paper, comparison of voting algorithms. And so this is a single decision tree. These are 3 different ways of doing bagging. I forget the little details that change, but you can see this part is the variance part. This part is the bias part. The bias part actually decreases slightly, but I think in general it stays about the same. The variance part, as you can see, goes down by a lot. Yeah, so why does bagging work? One way you can think about why bagging works is you can define an ideal aggregation predictor, which basically says, suppose I were given an infinite number of training sets sampled from the test distribution over a certain size, right? And I compute the prediction that's the average of all the models trained on these training sets. So if I were given actual access to the test distribution and I sample training sets of size of 100 or whatever this training set size is, then I could compute this quantity, which is the ideal aggregate predictor, right? So you can think about how the training set of any individual decision tree from a single sample of the single training set sample will compare versus the aggregate, right? And I won't go through the details like in depth, right? But the basic idea is you can use this sort of at least with squared laws, you can use the same arithmetic you use to derive the bias-variance decomposition, to sort of prove this quantity, right? Which basically says that you can upper bound the loss of the single decision tree. It will be always bigger than or no less than the loss of an aggregate predictor. And the details of this derivation, not too important, just leave it out there in case you're interested in looking at the detail. Right. The key insight is that the ideal aggregate predictor improves upon a single decision tree in expectation if it only, not if and only if this statement is true, right? And this is a large improvement if the model class is unstable. Bagging, on the other hand, has a different sampling process. You can write the exact same statements, but it relies on the assumption that this is true, right? Which is a statement about S prime being sampled from S with replacement. Right, so the bagging predictor improves it. The bagging predictor is more stable than S, right? And you could imagine some worst case scenarios where it's, less stable than S. Although usually that doesn't happen. Okay, in the final 5-ish minutes, I'm going to cover random forest, which is a quick extension of bagging, specific to decision trees. So the goal of random forest, again, is to reduce variance, right? And in some sense, bagging can only do so much because resampling of training data asymptotes, because you're just drawing samples from the same training set over and over and over again, right? The intuition behind random forest is that, okay, let's not just resample training data. Let's just not sample training data. Let's sample training data and features, right? So here's the procedure for random forests. We sample a training set S prime through bootstrapping from the original training set. And then we train a decision tree on S prime, right? However, instead of using a generic decision tree training algorithm, at every internal node in the training process, in the top-down training process of the decision tree, we're not going to allow the decision tree to look at every feature. And in fact, we're only going to allow it to look at some random subset of the features. And so we train this decision tree in a way that it's sometimes forced to not use the same features over and over again. Sometimes, in bagging, no matter, you generate a bunch of samples, but then the top split is almost always very similar, right? And here, that's not always going to be the case. And then after that, we do the same thing. We average the predictions of the learned trees. So this is a model extension of bagging that is specific to decision trees. Although you can imagine versions of this that can be extended to linear models as well. And the intuition is that this further decorrelates the trees that you train in each S prime bootstrap sample. Right, so you do training. You randomly only look at age. This tree. Randomly only look at gender. Randomly only look at age. And you can also randomly decide a number of thresholds as well, right? You don't have to look at every possible threshold either. Just to recap random forests, it's an extension of bagging to sampling features as well as training examples. Right? So at each leaf node, we only look at a subset of features. You can also subsample splits as well, and you average the predictions. And so this plot I pulled from this paper, which is an empirical evaluation of supervised learning algorithms. The take-home point I want you to take away from this plot is this brown line, which is random forests. And it does very well in practice. Yes?
But if you had one feature that was much more important, wouldn't it not do very well? Like if the certain features were more
If your sampling process was so it is a hyperparameter of the random forest learning algorithm, which is the fractional what fraction of features does the subsample from? Like do you randomly choose half the features? Do you randomly choose 75% of the features? So on and so forth. And the answer to your question is yes, if that fraction is too low, right? So there is a little bit of wiggle room for tuning the training algorithm for random forest.
So why is it called forest?
Because it's a bunch of trees. Yes.
Or, I guess for bagging, are you randomly sample was a smaller subset of your training data and you like train on a bunch of those on average?
You sample with replacement a training set of the same cardinality as your original training set, typically.
But then would you be like generating like new training sets or something?
You're generating new training sets, yes.
So like how would you be able to do that? Like normally you just collect a bunch of data and have a training set. How would you like generate new ones at random?
Well, you treat your training set as you treat your training set as the test distribution, and you define a uniform distribution over over that training set, which means you're sampling with replacement from it.
Ah, okay.
Okay, so next lecture, we're going to talk about an alternative to the flip side of bagging, which is called boosting, which is a method for reducing bias rather than variance, and then ensemble selection. And next week, we're stations on probability statistics.